So we're going to talk about what's called a discrete random variable today, and then eventually we'll talk about continuous. But the first thing you want to know is what's the difference between discrete and continuous? And the answer is the gaps. So if we look at what's called like a discrete number line, would just be points, let's say at the natural numbers like this. So discrete just means there's gaps in between. Versus continuous, so this would be like the natural numbers, right? Continuous is dense, so that would be like the real number line. Or if I filled in between, and we're looking at every number possible, and there are no gaps between numbers. Does that make sense? So you can choose any two numbers, and we can find infinitely many numbers in between them. So discrete has the gaps, and continuous does not. Continuous is infinitely dense. So when we talk about a discrete random variable, we're talking about a variable that takes on specific values that have gaps in between them. So we already actually defined what a probability model was in the last unit. And so this is just a model that describes the possible outcomes of a chance process and then also gives the probabilities that those outcomes will occur. So the thing I want you to write down is what's in green. A random variable takes numerical values that describe the outcomes of some chance process. And then the probability distribution of that random variable gives its possible values and their probabilities. So for example, here we're tossing a fair coin 3 times, and the variable that I'm defining is x is the number of heads I get in those 3 tosses. So the outcomes possible are 0 heads, so tails, tails, tails. I could have 1 head. There's 3 ways to do that. Heads, tails, 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 heads, tails, 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 heads. Or I could have 2 heads. Heads, heads, tails, heads, tails, heads, tails, heads, heads. Or I could have 3 heads. So the possible outcomes, the possible values are 0, 1, 2, and 3. So for my probability model, I would list those outcomes in the first row, and below them, I would list their probabilities. And we know it's a valid probability model because if I add up their probabilities, they add up to 1. So this is a little bit of review from last unit, although we are defining a new sort of term, which is random variable. It just is a variable that takes numerical values that describe the outcomes of some chance process. Yeah, so nothing super new other than defining what discrete is. So we're just going to do a couple of examples to talk about a discrete random variable. Usually we define them using a capital letter. All right, let's try this. So here we're given a probability model where X is the number of languages spoken by a randomly selected high school student. And so we're given the probability distribution here. And it says, show that the probability distribution for X is legitimate. And the way we would do that is just take 0.630 plus 0.295 plus 0.065 plus 0.008 plus 0.002. Toss that into the calculator, and we would see that that adds up to 1. And as long as your probability model, all the probabilities add up to 1, it is legitimate. One dumb thing that I do teaching remotely is like I realized this like last class, because I'll do this at school, but it makes sense because I'll like have my calculator under the dot cam and I want to be modeling what I'm doing. But I'll like type up what I just wrote up there. I'll type it into my calculator. Like I haven't taught this 3,000 times and I don't know that it adds up to 1. And you guys can't even see it. So there's no reason for me to be doing that. Okay. Make a histogram of the probability distribution and describe what you see. Oh, this is where I run into some trouble because normally I would have my whole whiteboard to do this with, but I don't. So I'm out of space. All right, so I'll just draw it right here. All right, so if we want to make a histogram out of a probability distribution, discrete probability, what we would generally do is, remember a histogram has bars. I'm going to just put the bars, I'm going to put the values in the middle of the bars in this case. So this will be 1, 2, 3, 4, and 5. Then on the vertical axis, I would have my probabilities, right? So let's see, in this case, it probably makes sense to go by, let's just go by tenths. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. And then we would just make the height of the bars match the probability. So 0.630, something like this. And in a histogram, the bars should be touching. In a bar graph is for categorical data. They wouldn't be touching, but in a histogram, they are. 0.295, so almost 0.3. 0.065, so now we're way down here. Okay. So something like that. We would want to label our X and Y axis. So this is languages. And then this is probability. And we would describe it the same way that we describe univariate data, right? So socks. So this is a throwback to way earlier at the beginning of the year, but it's shape, basically shape, center, spread, and then if there are any outliers, we would discuss outliers, right? So I'm going to go ahead and say the distribution, whoops, of languages spoken is unimodal, meaning one peak, with a strong right skew. When I talk about center, we'll talk about how to find the mean of a distribution like this in a minute, but remember that center can be basically mean, median, or mode, whichever is most representative. In a case like this, it's probably most representative to talk about the mode. So the most common number of languages spoken. So I'll say most students only speak one language, and then with some speaking up to 5. All right. Not really any outliers here, so I'm not going to discuss that. But I discussed shape, unimodal with a right skew. I discussed center, saying what most students do, speak one language, and spread. I talked about kind of the range that they can speak up to 5 languages, right? So I made sure to cover all the main points in SOCs. All right, what is the probability that a randomly selected student speaks at least 3 languages? So here we'll model some probability notation. We named this variable x, so the first one, at least 3, is going to be x is greater than or equal to 3, right? And so all I would do for that is add up the probabilities for 3, 4, or 5 languages. So it's just 0.065 plus 0.008 plus 0.002. All right, that comes out to 0.075. There's my probability. And then more than 3, the only thing that changes there is that x is strictly greater than 3, right? So in that case, I would just want to add up the probabilities that correspond to 4 or 5 languages. So that's just the 0.008 plus 0.002, and that's 0.010. All right. So there's our first example of dealing with a discrete random variable. Let's start talking about gambling. So in roulette is this one. And so you put a marble in, you spin the wheel, you put a marble in, and whatever it lands on, you can make a bet on. There's a bunch of different bets that you can make because there's a table next to the roulette wheel, and it's basically a grid of all the numbers that are on the roulette wheel, right? So there's 38 numbers on the roulette wheel, and it's 18 of them are red, 18 of them are black, and then 2 of them are green. There's 0 and 00, okay? And so they'll have these numbers all like laid out. I don't remember what the pattern is. It's not just like numerical order. It's like, I don't know, it's something random. And so something like this, and you can make all sorts of bets. You can bet on a single number, not smart, because you're not going to win. And but that pays out higher. So if you did win, so if you put like your chip down here, you bet on 1 and it lands on 1, you get a huge payout because it's really unlikely that that would happen, right? The most simple bet you can make is red versus black. And that basically pays out 1 to 1. So if you bet $1 and you win, you get your $1 back plus an additional $1. And the reason is that's like the highest probability that you have to win. And it's only like, it's like 48% chance basically, because it's 18 out of 38. So probability still is not in your favor, but that's the highest you can go. But one of the bets you can make is called a corner bet. And so that's where you take your chip and you put it on the corner on the table. So you would put it like right here so that it's touching all four of these numbers. And basically you're betting on all four of those numbers at the same time, right? And so the payout for that is 8 times your bet. And so I can create a probability model here, which is the net gain from a single $1 corner bet. And so the outcomes are this: either negative $1, meaning you lose your dollar because you don't win, or $8, meaning you get your dollar back plus an additional 8. And so the probability of each of these outcomes is 34 out of 38 that you don't win, and 4 out of 38 that you do win. A couple years back, what was that? It must have been 2 or 3 years ago. There was a conference in Las Vegas, a math conference that me and Kenton went to, and I was teaching statistics, and it was right around this time. So I was like teaching random variables and roulette, and I was like, this is a bad bet, but I'll make this bet when I go to Vegas just to show you guys. Anyways, I hit on the corner bet. I put $20 down and I won $160. So it wasn't the point I was trying to make to my stats students, but it was cool. All right. So if we were to make this bet over and over again, what would be the player's average gain? So here I'm trying to give you an intuition for finding the mean of a discrete random variable. But here's the idea. If you made this bet a bunch of times, let's say 38 times, in the chat, how many times would you expect you would lose? Let me just pick a random number of bets to make. Let's say you made 38 bets. How many of those do you think on average you would lose? Yeah, probably 34, right? So you would get negative $1 34 times, right? So I'll do negative 1 times 34. And then you would probably win about 4 of those times, right? So you'd get $8 about 4 of those times. And so if I average that out, so if I divide that out by the 38, that comes out to about, and I should use the approximate, negative $0.05, or about negative 5 cents per bet. Meaning, on average, you're going to be losing about 5 cents per bet that you place. This is on purpose, right? So remember that probabilities are only predictable in the long run, and there is only one entity that's playing for the long run, and that's the house. That's the casino itself, right? You're playing in the short run, so your outcomes are relatively unpredictable, but the house is playing in the long run, and theirs is absolutely predictable, meaning they will gain about 5 cents per bet placed. Now, 5 cents is a very specific number, and you'll come to see that in a lot of their games, that's what they have set the probabilities to be per hand or per play. And that's just because that's a number that is low enough that it's not killing the player, right? But it's making them money. So it's keeping people playing while making them money. All right, so let's see what we really did here is another way of writing what I just did is -1 times 34 out of 38 plus 8 times 4 out of 38. So all I did to find the average outcome is I took each outcome from my table and I multiplied it by its corresponding probability, and then I added them up, right? And that's exactly how we find the mean, or another word for mean is expected value of a random variable. You just multiply outcomes by probabilities, and then you go ahead and add them all together. Remember what sigma means. It looks scary, but all it means is add them up. All right, so it says calculate and interpret the mean of the random variable x in the languages example on the previous page. So let's do that. I'll just do mu of x equals, I don't remember. All right, so all we're going to do is take each outcome, multiply it by its corresponding probability, and then add them up. So I'm going to have to do this a couple times. 1 times 0.630 plus 2 times 0.2295 plus 3 times 0.065 plus 4 times 0.008 plus 5 times 0.002. And then I'll just go ahead and pop that into my calculator. And I get 1.457 languages. And so the way we can interpret that is in this way, and this kind of answers the second question, which is, the answer is no and no. The expected value or the average value does not have to be one of the possible values of the random variable, and it should not be rounded, because the way you would interpret it is write a long run average. So if we randomly selected many students, we would expect the mean number of languages spoken to be about 1.457. So just like we interpret any other probability, it's a long run relative frequency. So if you're ever asked to interpret, make sure that you indicate long run, which I did by saying randomly selected many students, right? All right, and that is of a discrete random variable. We're now going to find the variance and standard deviation. So remember what variance is. Variance is just standard deviation squared. So we'll notate it with sigma. We'll use the subscript to indicate the variable again. And then we'll square it. This is really what you want to write down. So you take each value, you subtract the mean, you square it, and you multiply by the corresponding probability. You do that for every single outcome, and then you add all those up. That gets you the variance. If you want the standard deviation, you would take the square root of that whole thing. The good news about this is you really won't need to do this by hand. I'm going to show you that you can use your calculator to do this. So we actually are going to use our calculator for more than just arithmetic. So you do need a good calculator, not just your 4-function Solar deal. Give me 1 second, I'm just opening my computer calculator. All right, this formula though, you also, I mean, you will need it. You don't need to have it memorized. It's in the formula sheet that you're given for the AP exam. All right. So let's go over how to use this. I'm going to skip this one. Let's go back to our red-black corner bets in roulette. They both have the same expected value, although I don't think we made the red-black. Let's do the red-black expected value. We did the corner bet, right? So remember I let x equal the corner bet. And we found out that the mean or the expected value of that was about -5 cents, right? Let's do red black. So I'm going to let y equal the red black bet. And I'll create a probability model for that. So we're going to do net gain again. So let's say you bet $1. Well, you'll either lose that dollar, or like I said, with the red-black bet, it's the most simple bet, so you get the least payout, which would be you get your dollar back plus an additional dollar, right? So whatever bet you make, you could win that much back. All right. Well, you're betting on either red or black, and I said there's 38 total tiles. 2 of them are green, 18 red, 18 black. So that means the probability that you win is going to be 18 out of 38, right? And the 2 green are really what puts the house in favor for you, because the probability that you lose, let's say you bet on red, well, there are still 18 black plus 2 green that you could lose on, right? So there's actually 20 that you could lose on out of the 38. We know this is valid because if you add up our probabilities, they do add up to 38 out of 38, or 1, right? So, all right, now let's compute the expected value, or the mean, for the red-black bet. So remember, the way you compute expected value is you take your outcome and you multiply by its corresponding probability. So I have -1 times 20 out of 38 plus +1 times 18 out of 38. We can just go ahead and throw that in our calculator. What you'll see is you actually end up with the exact same expected value that you had on the previous one, which was negative, whoops, negative 5 cents. Um, all right, which is on purpose. Like I said, they're trying to make it the expected value low enough to keep people betting, but they want to be winning money on average on every single bet as the house. So that's the way to do it. All right, so now let's talk about how to calculate the standard deviations, which, like I said, we could use that formula. It's tedious. So here's an example of how we would use it by hand, right? First, you have to calculate the mean. Then once you know the mean, like in this case, they found the mean is 8.128, you take every single value, every single outcome, and subtract the mean and square it, and then multiply it by its corresponding probability. Then you add all those up. And so this probability model is baby Apgar scores, which is like I don't know, some sort of a test they give babies. And the way you interpret it is a randomly selected baby's Apgar score will typically differ from the mean by about whatever the standard deviation is, in this case 1.4 units. But remember, that's how we always interpreted standard deviation. It's the typical deviation from the mean. But again, you don't need to do that by hand. We can do it in our calculator. So let me show you how you're going to use your calculator to do that. All right, for us, the first thing you want to do is go to Stat Edit, and we're going to edit a list. Whoa, I got a bunch of stuff in here. If you have stuff in your list, it's been a while since we've used this. Remember, you want to hit Clear, not Delete. If you hit Delete, that will delete the whole list. Just highlight the list name, hit Clear, and then scroll down. It'll clear it out. So let's do the corner bet first. What we want to do in the first list, we'll do the outcomes. So for the corner bet, the outcomes were -1 and 8. So you were either going to lose $1 on your corner bet, or you were going to gain $8, right? And the corresponding probabilities, hold on, I got to go back to that. I don't remember. Let's see, the corresponding probabilities were 34 out of 38 that you lose, and then 4 out of 38 that you win. So list 1, I did my outcomes. List 2, I did my probabilities. So now I'm just going to quit to the main screen, so second mode. Now I'm just going to do a stat calc. I'm going to choose 2 variable statistics. Oh wait, hold on. No, I'm not. Right, that's what we want to do. I'm sorry. So we want to do one variable statistics, but we want our frequency list. So we want to do one variable stats. We're going to do our outcomes as list 1. Our frequency list we're going to call list 2. And all this does is it's going to weight the outcomes with our probabilities. That's what we want. If you have an older version of the calculator, it won't give you this menu. What you want to do in that case is just this. You'll pull up one variable stats, and you'll just enter list 1, comma, list 2. The comma is right above the 7. And you can access list 1 and list 2 just on the keypad using the second thing, the second button. So you do still want to do one variable stats, but you want to, basically what we're doing is weighting our outcomes by our probabilities. And you can see the mean comes out to exactly what we computed it to be, about -5 cents, right? That's X bar. And the standard deviation is then about $2.76. All right, so I'm going to call that sigma x equals $2.76. And all we're saying is that on a random bet, we would expect any randomly selected bet to deviate from the mean by about $2.76, okay? All right, so that was for the red-black bet. Now let's talk about, or I'm sorry, that was for the corner bet. Let's talk about the red-black bet. So let's go back to our lists, and I'll just do this in list 3 and list 4. Our outcomes for red-black were you either lost your dollar or you got your dollar back and gained a dollar. So my outcomes are -1 and +1. And our probabilities, the probability that we lost a dollar, remember, was 20 out of 38. And that we won was 18 out of 38. Right, so we can practice this again. So if you pull up one variable stats, so remember the way to get there is stat and then calc. Then I just want to change this to my first list to be my outcomes, so that's list 3, comma, my second list to be my probabilities. So list 4 for me here. All right, you can see I do still have the same mean. My X bar is -5 cents. But my standard deviation now is about $1 if we round it. So a smaller standard deviation on the red-black bet than on the corner bet. And all that means is that on average, in the long run, you're going to lose about the same per hand on either bet. But in any one typical bet, you are likely to lose or gain more on the corner bet than you are on the red-black bet. So what does that mean practically? Not much. You're going to lose money in the long run on either bet, and you're going to lose about the same amount of money in the long run. But you're going to have higher highs and lower lows if you make corner bets, and you're going to just steadily kind of lose money if you make the red-black bet. I don't gamble much. I've gone to Vegas, a few times, and I don't mind playing roulette because it's simple. I get nervous around like craps, stuff where you have to play with other people. But there are people it's so crazy at the roulette table who think they have some kind of a system, like it's not completely random. And so you'll see them, you're allowed to move your chips around the table until the marble stops spinning. So people are like strategically placing chips all over this table as if it's not completely random. All right. I'm going to give you guys a second just to make sure you know how to use your calculator. Go ahead and calculate the standard deviation in this example. So just put your outcomes in list 1. Put your probabilities in list 2, and just make sure that you can access one variable stats. You know how to do that, because like I said, I highly recommend using your calculator to do this. Don't try and use the formula and calculate by hand. The only time you can run into issues is if you forget, if you just do one variable stats, your calculator will just default to computing that for list 1, which means it'll just compute that on the outcomes. So if you forget to put comma list 2, it won't give you the weighted standard deviation like you want. So go ahead, take a minute and do that in your calculator. You should get about 0.17. And the interpretation is if we randomly selected many students we would expect any one student to deviate from the mean by about 0.17 languages. And I think, I already gave you this note. The danger to be aware of when using the calculator to find the mean and standard deviation is make sure that you're listing both lists, the outcomes and the probabilities, so that your calculator is weighting the mean and the standard deviation by the probabilities, right? And so I said list 1, list 2. Obviously, if you put them in list 3 and list 4, then you want to use those, but just make sure you use both outcomes and probabilities in your lists. We're going to stop there. I'm going to save continuous random variables for next time. So I think we'll do that tomorrow, and we'll take the formative assessment and call it a day, and that'll work well because we have a short day tomorrow. So we'll do continuous random variables, and then I'll have us work on the formative assessment in class tomorrow.